Hello. Hi, everyone. Okay, please turn on your camera. Great. So welcome to today's lecture. We will talk about recurrent neural networks today. And today, actually, I prepared something interesting. So unlike regular reviews, actually, today we are going to do the exercise by everyone. So please connect to this website. And in the login page, you can choose either student login and teacher login. So please choose the student login. And in the room name, please type this, Lee3656. And then it will ask you to enter your own name. So please type your name there. And then you will see a question. So from my screen, I actually see the number of students who actually connected. And if you successfully connected, please read this question and type your answer.
Professor, can you show me the room name, please? Okay.
Yeah, Lee, Lee 3656. Let me type here as well. So for those who are late, please connect to the Socrative, this URL, and you choose login, then student login, and the room name is LEE3656. And you will see a question, and you can type your answer. So we have total 46 students in the room, and I see 33. Yes. Yeah, I'll give you 1 more minute. Please think about this answer and submit it. Let me know if you have any difficulty connecting. Yeah, so the link is this, and the room name is LEE3656. Okay. We have more students in the room. Why we have just 41? This is not an exam. You don't have to talk to your friends. Oh, yeah. Sorry for the typo. Yeah. Thanks, Jisok and Hisong. Oh, it was my fault. Sorry about that. Okay, let's finish in 10 seconds. So 7 more students, please type your answer now. Oh, 6 more. 5 more. Oh, yeah, more students are coming. Yeah, let's wait a little bit more because of my typo. 44. Okay. Okay, 4 more. Please finish in 10 seconds. Yeah, 2 more. 5, 4, 3, 2, 1. Okay, let's see. We have a lot of interesting answers. Let's see. Wow. A lot of creative answers. Let's ask to some. Yerim? Yerim?
Yes.
Yeah. Can you explain how did you get this?
Because we have no padding, and I remember that we did like 64 by 64 by 16 with filter 5 by 5 by 5. So I thought for the width and height, 64 minus 5 plus 1.
Yeah.
And we have, I thought we have 3 channels. And with 8 filters, so I answered like that.
Okay. Okay. Do you now find out what is missing in your answer? We are dealing with a video, which is a sequence of frames. So how many frames in the sequence that is missing in your answer, right?
Yes.
Yeah. Okay, so let's see. Jayan, Yu Jayan?
Yes.
Yeah, you answered 11, 60, 68. How did you get 11?
I write 12 wrong as 11. Yeah.
Okay.
16 minus 5 plus 1 is the answer.
Okay, just a mistake. Thanks. Okay, and Kyuha. Kyuha, are you here?
Yes, Professor.
Yeah, where did you get 14?
I just misunderstood the problem.
It's okay. Just please explain, how did you get 14? Just curious.
I think the filter size is 3. But the filter size is actually 5, so I just misunderstood the problem.
Okay. Then it makes sense. Okay, so many of you wrote actually the correct answer, which is 12, 60, 68. So again, the first one is the temporal dimension, so the number of frames we have in the sequence. So because we have 16 and we are applying 5 by 5 and we don't have any padding, so it will be 12. And the next two are the spatial dimensions, so 64 by 64. And we apply 5 by 5 without any padding, so it's 60 by 60. And the last one is the number of channels, the depths. So because, that is equal to the number of filters we are learning, not the number of channels in the input. It's independent of the number of channels in the input. Please remember that. So 3 should not be appearing in the answer, but this 8 should be in the end. So this is our notation. We are going to keep using this, the temporal dimension first, then spatial dimension, and then the number of channels. But in some papers, you may see some different combinations or the order of those dimensions. Okay, let's move on to the next question. Okay, 11 more, 10 more students. Please answer now. Okay, 8 more students. I will count 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Done. Okay, let's see. Okay. Junbom, you answered 14, 58, 59, 59, and 8. And 8, 14, 60, 60. Okay, this is the most common answer, I think. Yeah, Donggan, I told you that we should not have 3 in the answer because the 3 is the number of channels in the input, but in the output, we should not have that number unless we specify the number of channels as the same. So that is something you should keep in mind. Okay, let's see. I see some interesting answers. Huisong?
Yes.
Yeah, how did you get this? Okay. Okay, yeah, it's fine. Because we have the input size width and height is the same, and the spatial corner is the same, so the output size should be the same, right? Okay, and Junbong, can you explain how did you get 59 here?
I have mistakes in calculation.
Okay, yeah.
That's
what I guess too.
subtraction.
Yeah, okay, that's fine. It's yeah, it's okay. And Inhue?
Yes, Professor.
Yeah, how did you get this number 3 here?
Yeah,
it's I know it's confusing. So yeah, please make sure that you should not put the number of input channels in the output channels. That is always the case. We have to specify the number of output channels like this, 8.
Yes.
Yeah. Okay. Great. Other than that, it looks okay. Yeah, we have one more questions. So let's do this. Yeah, this is simpler. So let's do it quickly. Okay. Who is Mello? Jiwon, it's you? Yeah, okay. In the last semester, one of the students wrote her name as Fukuoka Gondal. So everyone was just really laughing. And we really didn't expect that she's the Fukuoka Gondal. But in this semester, I see just 2 random names like Hi. Who is Hi here?
Hi, Professor.
Okay. Yeah, okay. Let's finish this soon. Please answer. 16 more students. Okay, let's finish in 10 seconds. Please submit your answer. 3, 2, 1, done. Okay. So, okay. Okay. Konstantin?
Yeah.
Yeah. Can you explain how did you get this number?
I'm not sure. Apparently,
okay.
I missed something.
Yeah. So the difference
is
with
the same padding. Yeah, I didn't read the question.
Okay.
Yeah.
So yeah, without this part, actually, this is the same as the question number 1.
Yeah, I assumed. Yeah. I was wondering already.
Yeah. Okay. I think Seonghee made the same mistake. Everyone else looks good because this is easier, right? Just the same padding, so the output size should be the same as the input, except for the number of channels. So most students did a great job here. Junbom, you made another mistake here, or I guess this is a typo. Yeah. Okay, great. So yeah, this is the end of today's exercise. And let's see your score. So this is just automatic grading. So actually, if this is not exactly matching, it is considered as wrong. So I will not use this as a grading, but so for example, this is a correct answer, but because of these spaces, these are marked as incorrect. But yeah. So yeah, great job. Please do practice. This is actually the dimension matching is one of the easiest way to debug your code. If your code does not running and if it's more functioning, then please check if you are putting the right number of dimensions that you intended. So that will be really useful when you actually program something and debug some other people's code, or if you would like to modify others' code, then it will be really great strategy to use the dimensions. Yeah, so was it good? Cool. So yeah, let's start today's lecture. So far we talked about convolutional neural networks mostly, and today we will learn about some other types of neural networks. Probably many of you are already familiar with this, the RNN, recurrent neural networks. So if you are already familiar with this, please use this time as an opportunity for a review or recall. And otherwise, if you are new to this, this might be a little bit fast-paced, but please be familiar with this because we are going to use these RNN models for video understanding models in the next lecture. Okay. So let's see some types of neural networks. So this is vanilla neural nets for image classification. So this red is the input, and green is our neural network or some hidden states, and blue is the output. So we feed some input to the model, and then it computes something, and then it outputs. So this is the most basic type of neural networks that we are dealing with. And so far, we just talked about these kind of things only. So from today, we will see some more different types. Like input is a sequence instead of just a single image or some vector. For example, we are talking about the videos now. So video, as I told you, video is a sequence of images. So input is a sequence of something. The images can be 2D matrix of pixels, or it can be extracted features, or whatever it is. It is a sequence of something. So input is a sequence. So we use the neural network to embed these into the vectors. And then we combine these somehow to output something once. But unlike the pooling or the averaging or the max, here we consider its order. So these sequence is not just a set of images. We are actually would like to reflect its order observed in the data. So, for example, the sentences are a sequence of words, and the order of those words does matter, especially for languages like English. And for videos, it also matters because video has its own structure and storyline. So if we just randomly mix them, that doesn't make sense for many videos. So we'd like to keep track of these orders. So that's why we have these arrows here. So in the end, we feed all of these, and we are representing the entire sequence or entire video to have the representation. And then we have one output in the end, something like the class scores. So this will be discussed in today's lecture. Or we can also do this, many-to-many. So input is the video or a sequence of frames. So we feed these in that order. And our network takes it as an input, each frame as an input. And using the previous hidden states, we update its hidden states. And for every frame, we output something. For example, the class score distribution. So instead of classifying the entire video just once in the end, we can always classify each frame by frame. But here it's not independently each frame, but we actually take the context, which is the frames observed the previously. So that is called many-to-many. This is not common though. And another possibility is one-to-many. So one example is image captioning. So input is just one image, one vector or one matrix of pixels. And we would like to output a sequence of words, which is describing this image. So here, the input is the single instance, but the output is a sequence of something. That is also possible. And the most complex one is probably many-to-many. So the input is sequence and output is also sequence. So video captioning is a good example of this. So feeding the video with frame by frame. And based on that, we would like to output the sequence of words so that we can describe the contents of the entire video. So these two will be discussed in the next lecture, especially on image captioning and the video captioning. So let's see the basics of the recurrent neural networks, or for those who are familiar with this, this will be a good review of RNN. So RNNs have an internal state that is updated as a sequence is processed. So we have, before this RNN, we didn't have any kind of feedback loop. So everything was just one directional. So from the input to the output, we always has just a unidirectional relationship possible. But here we have some feedback loop like this. So in this way, this RNN module gets some input and uses its previous states as its input, and then it self-updates the current states using this most recent input and based on its previous states. And then based on the updated states, it outputs something. And then it gets the next input and repeats the same thing again and again. So here with this feedback loop, this blue thing, the new value is determined by its old value, which is this green, as well as the input, which is this red. So we can express this with this expanded view. So instead of that feedback loop, we can actually expand like this. So again, the input is a sequence of something like this. It's x1 to xt. So this model takes the first input token, and then it updates its internal state, and then it outputs the first output. And then it takes the next input and using the previous state as some kind of input to itself, and then updates it, then outputs y2, and it repeats until the very last token. So that is the how we expand this simple feedback loop into the entire sequence like this. in that sense, this is something similar to what we've done with the fully connected layers, because these are all connected in a unidirectional way. So from the input to the output and only from the left to the right. But here, what makes it unique is it has its hidden states, and the same hidden states are always being used. So if this is a fully connected, we should have some different values for all of these RNNs at each step. But we are always using the same tensor, and we just self-updates to change its value slightly based on the input and output and the gradients based on that. So the hidden states should be initialized to some value, because in the very first input, we will need its previous value and the input as its input. And then it updates to the next hidden states, which is called H1 here. And then based on H1, we output Y1. And then based on H1, we take the X2 as input. And based on these two, we update the hidden states. And that is called H2, and so on. So in that way, we can self-update this RNN cells based on the input and the previous hiddens. OK, so let's do this. Let's write this in mathematical formula. So we are taking a sequence of vectors or tokens, or whatever you call it, or images, x1 to xt. So these are the inputs. And that is processed by applying a recurrent formula at every time step. So this is actually just a mathematical representation of this diagram. So given an x at some step, it takes its previous hidden states of the RNN, ht minus 1, and we do something with the function within this function, and then it outputs the next hidden states. And that is written back to the RNN. So the main difference is here, as I told you, it is important to note that same function and the same set of parameters are used at every time step. So that is the key of this RNN. So let's see how it works. So inside this, I just told you that we are this model takes input token and the current hidden state, the previous hidden state, and do something on that, and then it updates to the new hidden states. And from there, we take the generate some outputs. So what should we do here? There may be a lot of different options, but we are using deep neural networks so far. So let's think in a similar way. So to make this, so let's do what we usually do with the fully connected layers. So one simple way is just taking the what we do with the fully connected layers. Given an input, we linearly transform it by multiplying some matrix W, right? And then what is followed? The activation function, nonlinear activation function, right? And then we output it. That is what we do with the fully connected layers usually. So here, we have two inputs instead of one. So for each of them, we apply the linear transformation. So the first one is from hidden states to the next hidden states. So we call it WHH. And from the input side to the next hidden states, we call it WXH. So we have two weights here because we have two inputs. And then we usually have the non-linearity here. So they use tangent hyperbolic function. So I don't know why, but that was the design from the original RNN. So we just follow that. And then we have the updated HT. And from there, we also apply the linear combination, linear multiplication, which is called W. Now from H to Y, so it is called WHY. So YT is computed based on that. So in mathematical formula, this looks scary, but actually that's exactly what I just explained. So these two are inputs, HT minus 1 and XT are inputs. And we multiply some linear matrix then we take some nonlinearity, and that is ht. This is exactly the same as what we've done in fully connected case. And then we use this ht and multiply with this w, hy, to get yt. So if this is the label that is a regression task, then we don't have any nonlinearity here, because the output should be any real number. But if this is some classification task, then we may have some sigmoid or something to make this between 0 and 1. So it can be adjusted. OK, so again, I emphasize that all the weights are shared across time. So these wxh and whh and here why are always the same. We don't have separate weights for each steps. Regardless of the index of the inputs, we always use the same w values, and the model should optimize to best reflect the relationship between x and y. And for that, we have to optimize these w's so that we can best approximate this relationship between the sequence x and the sequence y using these same values. That is the restriction. And that's how we actually can take arbitrary lengths of these input sentences or input sequences. So we'll talk about that later. OK, and then, yeah, gone?
Oh, I didn't really understand why the old weights should be shared. So can you explain it again, please?
OK, if we are to use different w's, then what does that mean? If we have some specialized w for this x1, that means we learn the relationship between x1 and y1, and we have separate relationship between x2 and y2, and another separate relationship between x3 and y3. If your task is more suitable with that kind of models, then actually you don't have to, well, you have less motivation to use the sequences, because each of these tokens have very strong relationship with each of these labels. But in this case, it's not usually. So we would like to learn the meaning of this entire sequence. And also, if we have the separate weights for each of these steps, then how many should we learn? Some sentence has just 3 tokens. Some sentence has like 100 tokens. And we don't know the length of the input. It's even more diverse in the case of videos. So they always share these weights to encode these inputs and apply to the sequence. And it's learning the general relationship when we process each of those tokens given the current states. Does it answer?
Yeah, thank you.
Yeah. OK, so because we are doing neural network and we are going to use the regular techniques called backpropagation to learn or train those models. So how should we apply the compare against the ground truth? So suppose we have the output labels for each of these steps, then we try to output which is the same as the ground truth token for each of those steps, and then we will compare them for every steps. So for example, if we have one-to-one mapping, so these are the video frames, and these are the tokens describing that video, then given this frame, then we will output some token, like this is a frame about cat, and we would like to match that is to the with the ground truth of describing this particular frame. And in the next token, next frame, we take the current state, the hidden state h1, and the image, and then we output what is this frame about, or what is this video about, and then we have the ground truth y2, so we match it. We'd like to match it. So that's the basic. But what if we have just one ground truth, like the many-to-one problem? So we have just video level ground truth, what the class it is. Then we don't have to output in the intermediate hidden states. So we just consume the entire sequence, and these H1, H2, and HT, these actually this HT consumed all this input sequences, and then it somehow extracted its meaning, and then the semantics of the entire video is compactly represented within these hidden states after consuming all of these input frames. And then based on this, we output. Sometimes we have some additional fully connected layers here. So we output the label for this entire video. And then we have the ground truth label for the entire video. So then what do we do? It's the back propagation, right? From here, we will have the loss. And based on that loss, everything here will be updated based from the back propagation, just as what we do in convolutional nets or fully connected layers. Okay? And sometimes intermediate hidden states may be also used when we determine the output. So that is because if this sequence is too long, then because we are feeding the input in the given order, it tends to remember the recent inputs better than the previous input, the earlier inputs. So these earlier hidden states are better representing the earlier inputs. So we sometimes concatenate all of these hidden states to learn or output these labels. So sometimes this is a useful strategy. And what about one-to-many? So one-to-many, we are giving just one input, one image, for example. And the entire networks consume just this, no steps, just one step here, right? Because the input is just one image. So then it starts to output something. But to output the sequence, just one sequence like this, we are in a trouble somehow. Can you see why? In the RNN, we always had some input, and so always we take the two inputs, one input token, some X something, and the hidden states, the current hidden states, and based on those two, it updates its self states and then outputs some labels, right? But here, because we have just one input here, we have nothing to give after that. So when we start to generate the outputs, so what we do is just putting the previous output as input. So after consuming this input image, then we start to output the first word describing this image, for example, and then we feed this word token as input to the next step. And based on that and the hidden states, it generates the next output. And we just repeat that. So after that, we feed this again. And from this hidden states, we update the hidden states and output the next token. And we just continue until some finishing condition. So in this way, we can input some image and generate the sequence of words describing this input image, for example. And then we will have the ground truth description of this image in the training data set. So that is given here, the purple colored Y1, Y2, and Y3. And then each of these comparison will generate some loss, especially at the beginning, those words will be different, right? So based on those loss, then we will backpropagate the error until the very first step from all of these. Okay, that's what how we update this one-to-many cases. So this kind of steps is called auto-regressive. We input the output from the previous step. So now this is the most complicated stuff, which is extension of this one-to-many to many-to-many. So input is a sequence, and output is also a sequence. So this is also called sequence to sequence, or seq to seq for short. So here, in the input, when you give the input, it's actually just taking the input and output nothing. It just stores the meaning or semantics of this input sequence in the compact representation of the hidden states. And in the end, in this H3, it will contain the entire semantics of this input video or sentence. And then, so this part is called encoder. So we use many to one as an encoder. So here we don't output anything because we are not simply just comparing against some labels, but we need to generate some output like this sentence. So use this H3 or the last hidden state as the initial state, hidden state of this decoder part. So in this decoder part, we take the one-to-many. So hidden state is initialized from this encoded hidden states from the encoder. So we expect that this S0 contains the semantics of this input video. And we start with some initial token. So it's a very special token that indicating this is the start of the sentence. Then it will generate some meaningful sentence describing this image once it's trained. So given that it will interpret like this. Okay, we are starting to generate some sentence because we got this. And the meaning of those sentences should reflect the meaning we can observe in this hidden state. So from that, it outputs this Y1 and updates the hidden state to S1. So this S1 will be different from S0 such that we still have the general semantics of the video that we are going to describe. But at the same time, we are giving this Y1 as input. So now we are describing this video, and so far we have generated Y1. So then it updates the hidden state to S2, and then outputs Y2, which is the second word, given this input word. So it repeats until it generates some special token, meaning the end of the sentence, for example. So we will go over some examples of this image captioning in the next lecture in more details, but that is just general idea of this sequence to sequence. And how do we train them? So it will be the same, the back propagation. So the loss is generated when we compare the generated sentence to the ground truth sentence, which is called, the Y's in the purple color here. And each of these will generate the loss, and they will be updated all the way through this RNN until the very first hidden states. So in that sense, it will be updated. And once it's trained, then it will be able to generate the meaningful description of the video once it's trained on large data set. So this is the TensorFlow API, the vanilla RNN. So well, it has a lot of options, and you can actually see that in the its page description here. But what you need to actually specify is this, just the dimensionality of the hidden states. That's only one thing. So for example, if you input this size of tensor, so 32 is the batch size, so the number of examples or the videos, and 10, the second one, the 10 is the sequence length. So your each video has 10 frames within it, and 8 is the feature dimensions here. So if you give this as an input and you use the RNN with hidden size 4, hidden feature is represented with 4 numbers, or a vector of size 4. Then once you train this RNN model, then it will output two things. So output sequence and final state. So output sequence is for every step, it is updating the hidden states. And that those hidden states are a sequence of the same length as the input, right? We input k tokens, then we have k hidden states in a row. So this output sequence is returned with those hidden states, sequence of hidden states. And the very last one is output as a final state. So what would be the size of this? We have 32 examples, right? And we have sequence of 10 frames. So the output sequence should be 32 times 10 times the number of dimensionality, 4, right? Are you following this? The input was 32 times 10 times 8. That means 32 is the number of examples, so it should be always the same. And 10 is the number of sequence. So it should be the same if you get the output sequence. The hidden state sequence should be always the same as the sequence of the inputs. And 4 is the dimensionality of those hidden states. And if you get just the final states, then it will be the very last element of this. So you don't need this 10 and just this 32 by 4. So yeah, I will not go into the details of these, all the detailed options. So please check this Keras website to see what they provide. And you may use them in your project or for your research. OK, so why RNN is good and why RNN is bad? Let's summarize that. So RNN can process input sequence of any length. That is the biggest benefit of RNN. A lot of applications like NLP, for example, the sentences, we don't specify the length of the sequence. Video is the same. Video can be arbitrary length. So this is really good aspects of RNN. Any length of input can be processed. And model size does not increase for the longer inputs because it always share the hidden states and the weights within the model. And computation at time step t, in theory, can use information for many steps back, which is, in theory, actually, it can process any length or arbitrary length of the videos. And it's expected to memorize or remember what was happening in the beginning. But yeah, we will see in the disadvantage. But in practice, it doesn't work like that, especially the sequence is too long. That's actually expected, or it's obvious, because we are using the limited capacity to memorize too many things. We have just kind of tape, and its capacity is limited, but we are trying to record too many songs there, then we have to overwrite at some point. So in that sense, actually, it cannot, its memory is actually so bad. So we will see more about that in the later. And same weights are applied at every time step. And the disadvantage, RNN is slow. It's really slow. And sequence output inference is hard to be parallelized because we have to, it has to have the previous hidden states to produce the next output. So it cannot be parallelized. It has to be sequentially produce the output. So that's one reason that actually RNN is really slow. And vanilla RNN suffers from vanishing gradient. We are going to see this in the more details in the next part of this lecture. And vanilla RNN often fails to model long-range dependence in sequence. So that's what I told. If the sequence is too long, then it forgets the information it got at the first. So this is really bad thing because we would like to deal with arbitrary lengths of the input, but actually it doesn't work if the input is too long. So we're going to learn about some upgraded version of RNN today to overcome this disadvantage. And before we finish the basic part, RNN doesn't necessarily be just a single layer. So from the input, actually, you can stack multiple layers of hidden states. And yeah, here, this is an example of 3-story RNN. So from the input and previous hidden states, you generate the next hidden states. But this one is also used to generate the next level hidden states. So 3 times, and then it outputs the actual output. So something like that. So you can always put more than one hidden layers in the RNN. So why do we use RNN? Where can we use that? So let me just quickly go over this. Image captioning is an example. So image is an input, and this is a single token, but output is a sequence of words. So we'd like to generate some sequence. So RNN is a good candidate for this kind of problem. Or for the video question and answering. So we take a video, which is a sequence of something, as input, and then we also need to take the question, which is a sequence of something, right? So both of these are sequences, and output can be either multiple choice like this, or it can be also generating some answers as a sequence. So everything is sequence. Two inputs are sequences, and the output it can be also sequence. So VQA uses a lot of RNN-based models, actually. And visual dialogue. So it's a kind of chatbot. So we can generate the reply based on the other party's previous writing. And sometimes it can also take some images or videos as inputs. So this is another example of using some sequence-based models like RNN. And this is more complicated thing, visual language navigation. So some robot is exploring some space, and it takes the video of the scene it actually currently see, and human gives some instructions, something like high-level instruction, like go to the third room from there and take a right turn there, and you have to pick something there. Something like that. So we give some instruction like this, turn right and head towards the kitchen. So it needs to recognize what is a kitchen, for example, or it needs to be able to count how many corners it crossed, something like that. So it's a very high-level task and very, very complex application. But RNN can be a useful tool for this kind of task as well. So actually, this is the end of introduction. So RNN is widely used in NLP because it deals with sentences, and sentences are a sequence of words. So it is widely used in NLP, but also in computer vision, especially when we deal with videos. So in our lecture, we are going to see some other examples of using RNN in multimodal learning in lecture 16 and 17 later in this lecture, in this course. And today, we are going to see some variants of RNNs to overcome some of its drawbacks. And in the next lecture, we are going to see some actual applications of these RNN-based models for video classification and action recognition. So, towards modeling longer dependence. So far, we learned about this RNN cell. So this is a new diagram of the RNN we discussed so far. So given the previous hidden states and the input, we multiply weights and then sum of them, and then apply tangent hyperbolic function. Then it's updated to new hidden states. So this is what we've done with RNN, and we can write the formula like this. So when we do the back propagation here, from ht to ht minus 1, it will be something like this. So we need this partial derivative, and ht minus 1 is inside this tangent hyperbolic function. So the left part is its gradients, and multiplied by its coefficient, which is WHH. So it will be like that. And we will see what it actually causes. So back propagation from ht to ht minus 1 multiplies by WHH, like that. And then we do this not just one step, but multiple steps from h0 to very long, like ht, where the t can be like 10 or 20 or even hundreds. So what we need is the partial derivative of the entire loss at t with regards to this WHH, to update these WHH parameters. It looks like this. From the very last step, ht, and then we need, by the chain rule, ht and ht minus 1, and so on until the very first one. within this. So from here, we have to update until this one. So this can be rewritten as this. So very first one and the last one is written like that. And in the middle, they are actually always the same. So this is same as what we calculated in the previous slides. Partial derivative of ht with regards to ht minus 1 is this tangent hyperbolic derivative and multiplied with whh. So that part can be rewritten like this. Then this whh is always the same. That's I always emphasize. Rnn always uses the same w, the parameters, all the time. So this is same as regardless of the time step. So whh can be outside, but because we have t minus 1 of them, so that is multiplied t minus 1 times here. Okay, so far it's just a simple math. But let's see what does that imply. So this is what we currently have. Let's see. This part is multiplication of something t minus 1 times, right? That is the tangent hyperbolic's derivative and input something. So this blue curve is the tangent h function. And when we take the derivative of that, it looks like this. And that actually picks at the input is 0, which is 1. And all other parts, the value is between 0 and 1. That means this part, we always multiply some value which is less than 1, but larger than 0, t minus 1 times. What does that mean? This will be getting smaller and smaller again and again all the time when we have multiple steps or long sequences. If we have 500 frames in the video, this will be multiplying 0.5 or 0.1 or something like 500 times. So this part will be really, really small. And what about this part? This part multiplies some same value, t minus 1 times, like 500 times. So if this is larger than 1, then it will be exploding. If this is smaller than 1, it will be also vanishing. So it's really hard to control. Only if this is very close to 1, it will be okay. But it's rare. In many cases, it will be either exploding or vanishing, which is a very, very serious and hard to control situation. So exploding gradients can be addressed by just gradient clipping. So if that is too large, like 10 to the 50, then we just cut at some points and some large enough value, but controllable. So gradient clipping can be applied for exploding gradients, but vanishing gradients is much harder to control because this is vanishing already. This is also vanishing. Then the gradients will not reach to the earlier inputs, and it will not be updated, even though it generates some loss. That is a serious problem. So what should we do? So before we talk about the solution, let's define some simpler notation. Instead of drawing all of these things, I'm going to use this small FC box. FC box is fully connected box, which takes these two inputs, and then inside this, it multiplies some weights to them, and then it's added. So this part is simplified to this FC box in the following slides. Just it's our notation. Okay. So this is what we currently have, the Rnn. Taking input xt and current hidden state ht minus 1, and then we have fc and then tangent hyperbolic, then output to ht. That's what we currently have with Rnn. And I'm going to explain Lstm, long short-term memory, which is great for longer-term memory. So probably you have heard this term many times, but you may not be familiar with what's exactly happening inside this. So I will try to explain that now. So what the goal is we'd like to overcome the drawback of RNN, which is weak to deal with long sequences. In other words, conveying the information we observed at the beginning or earlier stage to the eventually we have the hidden states of the entire sequence. So how should we convey those gradients or the information from long away to the beginning? So that's the main motivation of this LSTM. So currently the information follows like this. From HT, when you backprop, from HT, we has to go through this pathway to update this HT minus 1. Even though they are the same thing, we have to compute these and updates by that. So this is the main idea of LSTM. This HT is suffering from vanishing gradients because we have to go through this FC. What does it happen within FC? We multiply with WHH, right? And because we are multiplying those WHH many times, that is, when we take the partial derivative, that will be multiplied outside. And because they are, when they are smaller than 1, then it causes the vanishing gradients problem. So we'd like to avoid that. But this FC is needed, right? Because we take these input, and without this, then we cannot model the relationship between these. So instead of this H, we just forget about that. We add additional hidden states called C, or Ser state. And Ser state is similar to the hidden states. It is updated when we take each input. So from CT minus 1, we will update it to CT. But here, we don't want to have any FC or multiplying with some weight values. We just add this to that, and then just update to that. Then when we take partial derivative of CT with regard to CT minus 1, we don't have any W multiplied there. It's just summing. So it will not generate the multiplied WHH for every time. So it will not affect like the previous vanishing gradients. So that's the main idea of this. So they applied this. And then, even though the Ser state is for long-term memory, we still need some mechanism to control it. For example, if we read some multiple sentences, then when the sentence is done, then when we start the next sentence, then we have to forget what we had in the previous states. Or in the video case, we have a video, some long video, which has some sections within that with different topics. Something like news articles in the news. So for every news article, it will be changing the topic every time. So we have to have some mechanism to control that. So that's why they have this forget gate here. So this will be multiplied with some output from sigmoid function, which is between 0 and 1. So given the input and hidden states, it decides whether this current Ser state should be preserved or not by this forget gate. So if that is, if this model observes that the input is very different from the hidden states, for example, it will output large number in the close to 1 in the forget gate. Then this will be almost forgotten, and the new contents will be added more like 100%, which creates the new Ser state to start the new topic. So that's the forget gate. And in a similar manner, input part, this part, because the Ser state is basically the sum of the previous Ser state and the input side. So they also apply the similar kind of gates, which is called input gates here, to control the input side information. And another gate is written here to the output gates. So output gates is applied not to the Ser state, but it's to the previous original hidden states. So if the Ser state information is controlled to be reflected to the hidden states based on these output gates, and all of these three gates are in the same form. They are just taking the FC from the HT-1 and XT, and then followed by the sigmoid function, which outputs between 0 and 1. and then they are multiplied to control the cell states and the hidden states. So these are just, it looks complicated, but they are just gating. So given the topic, when we should forget or when we should update the input, it just controls its ratio. The main idea is we are just applying the CT-1 and CT. So this is the overall structure of LSTM. So we see that from HT to HT-1, in this flow, we has to have this FC within that route. So the WHH should be multiplied. And that causes the problem of the vanishing gradients. So from this highway, from CT to CT-1, as I told you, we don't have any fully connected layers multiplied here. So it's just multiplied with the forget gates numbers, but it does not directly multiply some weights to the CT-1. So in this way, the information in the CT can be more preserved in the previous cell states. And that's how they achieve longer memory, or yeah, basically the longer memory using this LSTM cell. So this is the summary of this model with mathematical formula, which is very straightforward just from this figure. So we have these inputs, 3 inputs, xt, ht-1, and ct-1. So forget gate is fully connected layer taking these 2 as input, right? So xt and ht-1, and we multiply some weights within the fully connected layer. So we name it as wf and uf, and bf is just a bias term for this model. So that is ft here. It, ot, they look the same, just look the same here. So they take xt and ht-1 as input, multiplied with its own weights called wi, ui, wo, and uo, and they also have the bias terms. So it and ot are created. So these 3 are created in the same manner. And then how do we update ht and ct? For ct, it is updated like from the previous cell state multiplied with the forget gate plus the input part. So input part is this. Tangent hyperbolic is the original input function. With these, wc and uc are the fully connected part here. And it is multiplied here, the input gate. So that is how we update the ct. And for the last part, this ht is updated based on this output gate and tangent hyperbolic of this current updated ct. So this is just mathematical summarization of this model. So let's summarize what is the LSTM here. With the cell states and uninterrupted gradient highway, that's what I told here, from this highway from CT to CT-1, LSTM can preserve long-range information better than vanilla RNN does. Because in RNN, again, we have to go through these fully connected layers when we update using the backpropagation. So here, LSTM can preserve the long-range information better, much, much better. So if the forget gate is 1 and input gate is 0, then the cell state is preserved indefinitely, and vice versa. If the input gate is 1 and this is 0, then it forgets completely and starts a new sentence or new topic. So in general, they will be controlled based on the data, and it will generally learn when should we stop the cell state and start the new topic based on the data, and it will adapt to the new test cases. But this is important. LSTM does not guarantee that there is no vanishing or exploding gradients. It just helps to reduce it and just provide an easier way for the model to learn long-distance dependencies, but it does not completely solve this issue. That is still the problem of these RNN-based models, because basically we are trying to embedding infinite amount of information in some limited space. So in nature, actually, that's not possible if the input is too long, like 10,000 or 1 million words to 4-dimensional vector, which is obviously not possible. But LSTM tries to reduce that problem to make it a little bit better and a little bit more practical in the range that we are interested in actual applications. Okay, and this is GRU, gated recurrent units, which is very similar to LSTM. And LSTM was originally proposed a long time ago, but this is relatively newer. And the author of this paper is actually the Korean, Professor Kyunghyun Cho from NYU. I think this was a paper while he was a student. He became really popular with this paper. So LSTM had additional cell states to reduce this problem, but they actually didn't. So no additional cell states, as in LSTM. So they still use just the hidden states like this. And they used another idea to introduce the highway, gradient highway. So here, from HT to HT-1, we still have a mechanism that it goes through without FC. So because it has just two gates, RT and ZT, it applies some convex combination here. But basically, that's very similar to what LSTM achieves. So you can actually compare this one and LSTM in more details from these papers. But basically, they are achieving the same thing. So one good thing with GRU is that we have less number of parameters. That means it's easier to train, and it's lighter model. So LSTM is still used as a kind of default model for LSTM, the RNN. But you may also use the GRU if you would like to actually faster computation or less parameters. And yeah, NLP-heavy problems consider transformers. We are going to learn about transformers in the later lectures, and we will discuss later. So this is the TensorFlow API for LSTM and GRU. They look exactly the same, just the name is different. Almost everything is the same, and actually they are really similar to what we've seen in the vanilla RNN. So if your current code is using the RNN, then you can just change it to LSTM. Then that will still work. So still, you have to just define the number of units, and that's it. So it's just how to use LSTM. It's same as RNN, but it provides the way of long-range dependency. And today we learned how it actually works. So in practice, just use LSTM or GRU. So that's it. Okay, thanks for your attention. And yeah, you can ask questions now.